Alrighty, so we're going to take a look at section 1-9, inverse functions. So talking about an inverse. Mathematics is made up of functions and their inverses, or relationships and their inverses. Every function that we have has its opposite operation, something that undoes it, or an inverse. So like squaring and square root, multiply and divide, add, subtract. It's a really common thing. If we have a function, we need to be able to undo it, go in the other direction. So that's the focus of our conversation here today. So the essential question for today, how can I find inverse functions informally, meaning using things like tables, graphs, things like that. We'll get into the algebraic rule part in part 2, and be able to verify that two functions are inverses of each other. How do we know? So especially looking at like tables of values, like that numerical approach, and then the graphing approach. So use graphs to verify that two functions are inverses. And we're going to talk about something called the horizontal line test. Super cool test. For mathematicians to be able to determine whether a function, where its inverse is going to be a function as well. So we have a vertical line test to check to see if an original function is a relationship is a function. We have the horizontal line test to help us determine if a function's inverse will also be a function. So those are our essential questions for today. All right, so let's start with what an inverse function is. When we talk about opposite operations, it says for a function f, so they're going to use f again, that's defined by a set of ordered pairs. So remember, just like the relationship, x's and y's usually, but like first coordinate, second coordinate, to form the inverse function, all you have to do is interchange those coordinates. You switch the x and the y. So you interchange the first and second coordinates of each ordered pair. So for a lot of people, I think they just think of it as switching the x and the y, or switch the domain and the range, switch the input and the output. Remember, they don't have to be x and y. It depends on what real life application you may be using. But we just switch, interchange the domain and the range. So the x's become y's, the y's become x's. So here's the notation that we're going to be using for inverse, just so you can be familiar with that f inverse. It kind of looks like it's an exponent. It is not. When you see that little -1 up there, it does not mean 1 over. It's not a negative exponent. It means actually inverse, which I know can be confusing. So just when you read that, f inverse, that's talking about the inverse or opposite operation of a function. So the domain of the original function then would be the same as the range of f inverse. So the domain of the original function becomes the range of the inverse. And the range of the function then would be equivalent to the domain of the inverse. So the x's and y's switch. That's all that means. So it's pretty straightforward, I guess, if we have a relationship and we want to try to find its inverse if they're just giving us a set of ordered pairs. So let's take a look at this additional example. First of all, let's look at this set of values. Would you consider this to be a function? I know that the question is saying it is, but my question is, do you think this original set relationship is a function? Remember the definition of a function. For every x, it's paired with, fill in the rest, exactly 1y. So for every domain variable, it's paired with exactly 1y. No repeating x's. So let's take a look. We have 1, a 2, a 3, and a 4. Yep, we're good. This is definitely, yes, a function. All right, so how would you find its inverse? You switch the domain and the range. So the inverse function of f. So say we call this original function f. Let's call this f inverse then. So we'll try to use that notation. It's a set of ordered pairs where we just switch the domain and the range. So see if you can write down, pause the video, what do you think the inverse should look like, and then come back and check. So hopefully we realize that would be 5, 1 then, 6, 2, 7, 3, and 8, 4. Now the big question then is this new relationship that you just made, is this inverse also a function? So let's check, for every x is there's exactly 1y, or for every domain is there exactly 1 range? In other words, no repeating x values? Yep, so this, in fact, this relationship is a function itself as well, because we don't have those repeating x values. So we have to take a look, though. If we create a new relationship, we have to double check and make sure that it would be a function as well. They're not always going to be. So if you want to find an inverse, you just switch the domain and the range. You switch the x's and the y's. So if it's a numerical representation, that's all there is to it. All right, so how do you verify functions are inverses of each other if you don't just have a set of ordered pairs? Gets a little bit more involved to do it algebraically. We're going to get a lot more into this in part 2, but in order to understand if we switch the domain and range around, if we are actually having that relationship, we use composition. So remember our open circle. So compose, and we'll be writing this out using the symbols here in just a second. But to check to see, to verify, to show that two functions are inverses of each other, we compose f and g and G and F, so we do the composition in both orders, both should equal the identity function. Now, see if you can remember back from your parent graphs, flip back. Which one is the identity function? Go ahead, pause the video, see if you can find that. Which parent graph is the identity function? All right, hopefully you found that that was y equals x. So they should be equal to x, or in other words, if you do an operation and then it's inverse, you should get back to x, or the original value you started with. Let me give this a try for you. So I want you to think of a number. So pick a number, an easy number that you can work with easily. All right, I want you to multiply your number that you picked by 3. Okay, you have your result. Now take that result and now divide it by 3. Well, what did you get back to? The number you started with, of course. So if you do one function and then its opposite, right, multiply and divide, you should get back to what you started with, or that identity. So you should get back to x. So how does that look symbolically? So this was kind of a verbal description. That means f composed with g of x and g composed with f of x are exactly the same, and they should be equal to x. In other words, they undo each other. So the way to check is we do those compositions, and that's something that we're going to be dealing with in part 2 of this section 1.9, even more so. But we're going to try one in this part 1 as well. So we'll be doing a little bit kind of in both pieces. So focusing on the rules, or how do we verify or show that they are. All right, so let's take a look at the two functions. We have f of x, which is a degree 1 linear equation, and then we have g of x, which is a degree 1, again, linear equation. What we're supposed to check is, are these functions inverses of each other? So what that means is we need to do f composed with g, and then we need to do, we'll pick a different color here, g composed with f, and we're going to try to see if they undo each other. In other words, are they both equal to x? So let's go ahead and set these up and see if you remember what composition means here. So if we're going to do f composed with g of x, that means f of g of x. Or that means we're putting g of x, that linear equation, into the equation f for the x. So we're doing composition. This is one of the applications of composition. So that means we're doing f of this x plus 3 over 2. All right, let's go ahead and do that arithmetic and see what happens. So the rule for f of x says, hey, take 2 times what you substitute and then subtract 3. So 2 times what I substitute, and then plus or minus 3. Sorry, that's a minus. All right, let's simplify that and see what we come up with. So when I do this simplification, when I multiply by 2 over 1, the 2's would divide out. I get x plus 3 minus 3, which is just x. So that's making me feel pretty good that f composed with g of x is x. I get the identity function. Let's go the other way and double check and see if that is the case as well for g of f. Remember what that means. That means g of f of x. The second function gets substituted. So that means I'm taking this function f and I'm replacing it in for the x in the function g. So I'm doing g of this 2x minus 3. I'm going to substitute 2x minus 3 in for x. So in the g of x rule, I'm going to plug in for right here 2x minus 3, and then we have the plus 3 and over 2. Let's go ahead and do that simplifying and see if I get the same thing. In this one, in a fraction bar, remember you do simplify everything on the top and bottom first and see what you get to divide last. So the 3's would add to 0, so we get 2x over 2, so we get x. So g of f of x is equal to x, the identity function. So what does that mean? It means they undo each other. The operations of the one function undo or is the inverse of the other. So because f composed with g and g composed with f of x are both equal to x, they are inverses. All right, I want you to take a look back at the original equations now. We're going to talk about this, and we're going to also graph it too. What is the slope of the function f? Think about the slope there. The slope of that equation is 2. Let's take a look at g of x. I know it's written a little bit wonky, but if you divide that out, that's x over 2 plus 3 over 2, kind of in that mx plus b slope-intercept form. So the slope for this one would be 1/2. What do you notice about those two slopes? 2 over 1 and 1 over 2, reciprocals. Inverses, right? So if the original line has a slope of up 2 over 1, its inverse is going to have to be up 1 over 2, right? They're opposite operations. What was the x becomes the y. What was the y becomes the x. Because remember, we switched the x and the y. So think about slope, rise over 1, y over x. If you do its inverse, it's the x value over the y value. So we're thinking about that opposite operation, and we're subtracting in one, we're adding in the other. Yeah, because they're inverses. Take a second, type these two equations into y1, y2 on your graphing calculator. All right, I want you to take a look at those two lines for a second. So reciprocal slopes. So we look at that inverse idea. I'm in regular window, negative 10 to 10. I'm going to do zoom number 5, which is square, which makes sure that the scale is such that it doesn't kind of skew your vision because the screen is a little bit longer. So make it a square scale in terms of the tick marks or the intervals. So you can really see the relationship well between these two lines. There's a special type of symmetry that's going on between these two lines, and I'm wondering if you can see what it is. We're going to do another graph, and then we're going to talk about it again. So think about what relationship might be happening between these two lines. All right, so we talked about how to show, actually verify that two equations are inverses of each other. It's composition, and the graphs, like we just saw, will always have the relationship that we're seeing there. All right, so let's try another graph. Let's do this additional example to do a different paragraph. So those were linear. Let's talk about what inverses of a parabola might look like. So I'm just going to have you think ahead. What is the opposite operation of squaring? Square root. So I want you to think about that as we look at the picture that we get. So we're going to graph this function, f of x equals x squared plus 1. And then we're going to see if we can figure out a way that we could, without even having the equation. So notice there's no equation for the inverse. Would you be able to graph it? All right, so let's see if we can graph x squared plus 1. Now, you might know some things about the graph. This is a parabola, so it's going to be that U shape. Do you remember what the plus 1 does? Well, remember that moves the whole graph up 1. So if you have that kind of understanding, you can probably make a sketch pretty easily. But just to really clarify this, or f of x if you'd rather here, let's put in some values. So let's do -2, -1, 0, 1, and 2. Let's just get some good numbers in there. So go ahead, pause the video, fill in your chart. All right, so we're going to graph those points. So we have 0, 1, 1, 2, 2, 5, and then the symmetry on the other side, those same ordered pairs. Domain is all reals. Range for this one would be all the values greater than or equal to 1, because this graph is shifted up 1. So this is our function f of x. Now notice I'm saying it's a function. Why? It passes the vertical line test. So if I take a vertical line and I pass it across this graph anywhere, it's only going to touch 1 point, right? I'm only going to have that one value. Now, if I'm going to try to take a look and see about its inverse, we have to think about what we know about inverses. So remember, the idea of an inverse is that you switch the domain and the range. So let's talk about what f inverse would look like. Now, in order to find an inverse, it said you switch the domain and the range. Well, if you have a graph, you have ordered pairs. So how about taking this list of ordered pairs, and we're just going to switch the domain and the range. Now, the x and y, or domain and range for the inverse, then would become 5, -2, 2, -1, 1, 0, 2, 1, and 5, 2. You are just switching the domain and the range of that original function. Let's graph those points and see what happens. So we have the point 5, -2. We have 2, -1. We have 1, 0, 2, 1, and 5, 2. And we get a graph that looks something like this. F inverse. All right, so remember what I asked you, what's the opposite of squaring? And we said square root. The square root function would be the same green graph except without the one down in quadrant 3. So if I didn't have this spot down in quadrant 3, so we'll cover that up for a second. If I didn't have that part down in quadrant 3, that's that square root function that we talked about. So like this equation. So y equals the square root of x. Parent graph, right? We talked about that one. We call it the square root function because if you look at just the green graph the way I have it written, it would pass the vertical line test. If I ran a vertical line anywhere along this graph, so oops, that wasn't quite vertical. If I do a vertical line, it only touches 1 point right at each of those locations. So when I do the actual inverse of this original function, though, I actually do get both parts of that graph. So I'm getting the true inverse of what squaring is if I have that plus or minus idea for the actual inverse, which would be all those ordered pairs. So we kind of eliminate part of that to make sure that the parent graph itself was going to be a function. But for this, the true inverse of x squared is all these ordered pairs. So take a look at that green graph. Would it pass the vertical line test? So if you take a vertical line and pass it through any of these, how many points are you going to touch? Well, you're going to touch more than one. You're going to actually touch 2, one on the top, one on the bottom. That's not a function. So the inverse is not a function. So just because we switch the x and the y doesn't mean that new relationship is going to be a function. Okay, so my question to you is what do you notice about those two graphs? Same kind of situation is what I hoped you noticed when you looked at these two graphs. What relationship does the original graph have with its inverse? Well, it's a symmetry, it's a fold. Can you see it? It's a fold line. If you fold over the line, y equals x. So if I went ahead and put in y equals x here, 1, 1, 2, 2, 3, 3, 4, 4, this fold line, y equals x, the symmetry is true for every function at its inverse. I'm going to go back to our graphing calculator and I'm going to put in a y equals x there. You can do that as well. Look what happens. Yeah, they fold right over that. So that idea of switching the x and the y are always going to give that symmetry with a function and its inverse. So think about it this way. I have a graph as an example so you can see it. We have that y equals x. So we have the function and its inverse. If you have the point AB on the original function, that means you're going to have BA. Well, yeah, you switch the x and the y on its inverse. So if you have the point AB, then you're going to have the point BA and vice versa. So a function and its inverse is always a reflection over the line y equals x. That will be true. So that's a way to be able to identify functions, right? We can look at the graph and the potential inverse graph and see if they have that symmetry. We can use the table. We can look at the values. So I'm going to go back to my graph here so you can see that. I'm going to go to my table. You can see, ignore the y3, that's just y equals x, but look at the points in the table and you can see those flips. So if you look at the point, that's 7, 4. Oh, I'm going up by, yep, so I have the, or not 7, 4. So I have the point 4, 5. Then I also have the point 5, 4 on the inverse. So you can tell that you have that switching happening, and there's lots of examples of that throughout the table. It's somewhat easier, I think, just to look at the graph and say, oh yeah, there's that reflection. And that's true anytime you have a function and its inverse. All right, the other thing I want to talk about today is there a way that I could have known, and I'm going to go back to this graph right here, my x squared graph. Is there a way I could have known that f inverse, the green graph, was not going to be a function? We proved that it's not, right? It doesn't pass the vertical line test when we switch that domain and range. Is there a way that we could have known before we even started that that inverse wasn't going to be a function? The inverse relationship is true. It's there. I'm graphing it, but it's not a function. Could I have known that from the blue graph right away? And there's a great way to do that. It's called the horizontal line test. So the way to tell if an inverse is a function from the original function, use something called the horizontal line test. So basically, it's the same as the vertical line test, but it's checking to see whether the inverse of that function is also a function. So a function has an inverse that is also a function. Remember, every relationship has an opposite operation. The only way it's going to be this special kind of relationship that's a function is this. If and only if, very declarative, no horizontal line intersects the graph of the original function f. So we're starting with that original function f at more than 1 point. Okay, so think about that for a second as you look back at this blue graph. So that means if I'm taking a horizontal line, I'll try to use a different color here, and go across. So take a peek. If I pass a horizontal line across that blue graph, how many points does it touch? Well, 2, 1 on each side, right? 1 and 2. So that means I know when I switch the domain and the range, I'm going to have those repeating x values. Because remember, the outputs for the one function become the domain or the inputs for the other. So if I have two outputs on my original function that are the same, I have 5 and 5. That means for my domain over here, I'm going to have 5 twice. So we're going to have those repeating values. So it's a really quick and easy way on an original function to be able to know something about the inverse. So if your graph touches more than 1 point on a horizontal line, that means its inverse is not a function. All right, so basically what that means is then we talk about something that's one-to-one. If you are going to have an inverse that is going to be a function, it means there's no y values that repeat, right? So there's no y values that are going to be repeating because that means when you switch the domain and range, the x's would. So each dependent variable, the y's, corresponds to exactly one independent variable x. No y values repeat. So it's that kind of understanding of definition of a function, but for the inverse. So we have to think about what would happen there. All right, so it says a function f has an inverse. That's a function if and only if it's one-to-one. In other words, we can't have any y values repeat on the original function if our inverse is going to be a function. So I want you to think about what parent graphs would have inverses that are also functions. So if you think through your parent graph list, so if we think about linear, so we talk about slanted lines, parabolas, absolute value, rational function, or the cubic function, rational function, so the 1 over x, greatest integer. Which of these would have inverses that are functions? Can you go through the quick pictures that I just drew and see if you can kind of do the yes, no on each of these? All right, let's see what you thought. So think about, we're doing horizontal line test. Only touches at one place. The inverse is going to be a function. So the inverse is going to be a function for all slanted lines. We saw that on our first one. If we take a look back at our graphing calculator, when we did the two linear equations, I'll go back to my graph. Looking at the red line and the blue line, they're both functions. Slanted lines are just fine. The inverses will also be functions. How about the parabola? Nope. Crosses at two places, inverse will not be a function. How about absolute value then? Same problem, right? You have two y values that are the same. Actually, the inverse of an absolute value is the sideways v then, because remember we have that symmetry over y equals x. How about a cubic function? Totally good. Horizontal line only touches one. What we're checking for, remember, to see if the inverse of each of these is going to be a function. So cubic, its inverse is actually cube root, and it goes across. So where the cubic goes up and down, the cube root goes across. How about the rational function 1 over x? Only touching one point, so its inverse, that's also a yes for its inverse being a function. So cubics, rational, definitely yes. Parabolas, absolute value, inverse are not functions, so being able to tell. All right, so take that kind of train of thought, and we know we have some kind of parent graphs that are and some that inverses are not functions. How about this one? You may not remember what degree function this is, but it's a polynomial. What do you think? Does this inverse relationship, is it going to be a function? So think about our horizontal line test. How many points are you going to cross? 1, 2, 3. No, the inverse is not going to be a function. So the inverse is not a function. The horizontal line touches more than one point. So it fails a horizontal line test. I'm going to abbreviate there just a little bit. So let's go back to our essential questions here and see how we're doing. So how can I find the inverse functions formally or informally and verify? Okay, so we switch the domain and the range, right? We take the x and the y's and we switch them. That's how we find what the inverse is. How do we verify that they're functions? We do the composition. F composed with G, G composed with F. They both have to be x. Use graphs to verify. They have to have the symmetry y equals x, and we can see that relationship. And then use the horizontal line test to determine whether the function has an inverse that's also a function. So remember, if you have more than one y value, that means you're going to have more than one x value on the inverse, and it won't be a function. So we have some really great tests for inverses.